Hello, my name is Virgil Kohlberg and this is my Physics 2212 Lab 4. So as a little introduction, the purpose of this lab is to understand ohmic and RC circuits, so from very simple circuits to more complex circuits with capacitors and resistors. It is then to compare the mathematical predictions to experimental models, and it's also to compare different circuits with slight differences to see what impacts what variables. So as the main results, we've seen that the current in the simple resistor circuit is of 0.2 amps, and in the RC circuits, the RC value is of 5.98. We'll see that there is a similarity between estimates and find it very similar with very slight differences. And so for some of the fundamental concepts, we need to know about the node and loop rule, Ohm's law, and capacitance that we'll come more into later. So here are the equations. The node rule basically says that it's the conservation of charge. The current going into a junction must be equal to the current going out of a junction. The loop rule is the conservation of energy. Throughout the loop, the change in potential energy of voltage must be equal to 0. Ohm's law relates resistance to voltage and current, and the resistance, so a resistance in series will be found by this equation, while the resistance in parallel, while resistance in series will be just the sum of the different resistance. The capacitance is the division of the charge over that capacitance divided by the change in voltage between the two plates. So in a simple circuit, we'll see that the system is the voltmeter / ammeters, depending on what we're measuring, and this will be recurring throughout the entire experiment. The surroundings is the circuit. This is what applies, let's say, energy charge to our system of ammeters and voltmeters. So the circuit is simple. It's two 1.5 volts battery, a 48 and 100 ohm resistor, and 2 amperes. The predicted current was of 0.204 amps. The real one was of 0.02. There was a mistake writing here, and the reversed is of minus 0.2 amps. And so we can see that it's very similar, and that the only thing changing really is the significant figures. It cannot go that far in significant figures. So now we have an open circuit, so we've replaced one of the ammeters by a voltmeter, and so we can see that the voltage difference is of 3 volts because it's an open circuit. So it loses all of its, because the voltmeter is of infinite resistance, it loses all of its voltage over this gap, and there's no longer any current that reaches the ammeter. So here are the potential differences at the different spots. We can see that between A and B it's 3 volt because it's gaining that voltage, and then from C and D across the first resistors, and then E and F across the second resistor lose voltage. And from the loop rule we can see that this is consistent because it's equal to 0, hence the loop rule is applied and is correct. So now if we put an ammeter in parallel to the 100 ohms resistor, the current changes from 0.2 to 0.6 amps. The flow of electrons bypasses the resistor, hence the current increases, because instead of going through the resistor, it goes through the easier route, which goes through the zero resistance ammeter, hence increasing the current. So calculating resistance, we've seen that the R of the 47 ohms resistor is 48 ohms, of the 100 is 102 ohms. The wire and the ammeter are both 0 because they're ideal wires and ammeters. And we can see that there's a slight change, and this is because of the decimal places of the current, because we've seen that in reality 0.024 instead of 0.02. So here is the RC circuit. So we have a 9 volt battery connected to a 10 and then 20 ohms lamp and a 0.2 Faraday capacitor. So the current is always 0, as is with an RC circuit. So the time to charge and discharge can be found here. So we can see that the greater the resistance means a longer charging and discharging time. So if we want to determine the time constant of RC circuits, we have to plot the ln of voltage over the initial voltage over time. So here we have time, here we have the ln of V over VO, and the gradient, and from the gradient, by taking the negative inverse of the gradient, we find RC of 5.98, which is very, very close to the real RC of 6. So there's the source of difference is, it should be exactly the same everywhere, because we're using a computational model which is completely ideal. The only differences are problems are human error with me stopping and starting the stopwatches, as well as the significant figures, but overall the results are extremely similar and extremely accurate. So what if we turn everything into real life. So the ammeter and the wires would have non-zero resistance, so the current value would be slightly lower because it would go through more resistance. So what if we just had the capacitors with no resistor anywhere? Well, in the simulation with no resistance, the capacitor would charge instantly. But in real life, we have a slight resistance in the battery and the wires, and this would make it not instantaneous, but very, very quick. Thank you very much.